All right, so we're gonna take a look, just to revisit really quickly some of the stuff we saw some from last week. That we use, it seemed that people maybe generally didn't quite get. So we'll kind of review some of the exponents, working with exponents, and then also we'll take a look at scientific notation. So as a quick reminder, if I have the following expression, let's say that we had x 7 times x to the 3. And when you multiply these, what we do is we add the exponent, so that's x to the 7 plus 3, that would be x to the 10. If I were dividing these, so x to the 7 divided by x to the 3, then that's the same as subtracting the exponent, so that would be x to the 7 minus 3, the x to the 4. Right, so when you have a problem or a situation like these and you need to solve these um, equations relative to x, this is what you should end up with. I think several of you, when you did your the questions on the quiz, you ended up with an actual number. Well, you don't know what x is. You can't really solve that. You can only get it to the or simplify it in terms of x, right? So just keep that in mind if you're doing these types of questions. So if you take this, we extend it further an actual number now. So instead of x, let's say we have 10 to the 3 times 10 to the 4. Okay, so that'll be 10 to the 3 plus 4, which would be 10 to the 7, right? And that's an actual number. This is the same as saying 10 times 10 times 10. So 7 times 1, 2, 3, 4, 5, 6, 7, and that would be 1 and 7 zeros. So 1, 2, 3, 4, 5, 6, 7. So this would actually have a value, if you're given just x's or y's or something like that, you would just simplify it based on what x is. Okay. Again, if I had 10 to the, let's say 10 to the 10 to the 3 divided by 10 to the 5, this would be 10 to the 3 minus 5, because I'm dividing these, so I can subtract the exponents. That would be 10 to the minus 2, and this is the same as 1 over 10 to the 2, right? Which is the same as 1 over 10 times 10, which is the same as 1 over 100, which is the same as 0.01, right? And if we go all the way back to these and we extend or expand these out, we have 10 times 10, that's 10 to the 3, divided by 10 times 10 times 10 times 10 times 10. Okay, so these 10 can cancel out. And guess what? I end up with 1 over 10, which is the same as what we had up here. Right, so 1 over 100, the same as 0.01. So this is just, these are just shortcuts that we use to get to the same endpoint. You can by all means extend this out or expand this out and then solve it, the long way. But this is just a quick way to get to the same answer. And as long as you know how to work with these exponents, when you divide them, you subtract, when you add, also when you multiply, you add them, and you can get there fairly quickly. What about if I had 10 to the 3, and then I square this, right? So if we expand this out, what I end up with now is 10 to the 3 is 10 times 10 times 10. And then I'm going to square this. I'm going to multiply it by 10 times 10 times 10 as well, right? So this ends up then being 10 times 10 times 10 times 10. So 1, 2, 3, 4, 5, 6. This is the same as 10 to the 6. So the shortcut here is if you have a number raised to a power, this ends up being 10 to the 3 times 2, which is 10 to the 6. Well, that's the shortcut. You end up getting to the same endpoint, but you can by any means expand that out and solve it that way as well. So just a quick revisitation of some of those topics. It looked like that tended to give a little bit of issue, a problem last week. To make sure that we get that squared away as we go forward into a little bit more deeper math. So the other thing I wanted to talk about here was the use of scientific Again, we're dealing with numbers here, so you know how we represent numbers, and then we're going to use a technique called scientific notation, or sometimes it's called exponential notation. We usually use scientific notation or exponential notation. Sometimes we abbreviate this as psi naught. We don't even write the whole word. We use these or this when we need to express really big or really small numbers. Yeah, when it comes specifically to chemistry, we're going to be looking at things that are really tiny, things like atoms and even subatomic particles. And because they are so small, you know, you're going to need a huge number of them to actually make up the amounts that you see on a regular basis. So let's see how we can um, convert numbers that are really big, really small into the scientific notation. So let's say I have the following. Let's say I had a fairly sophisticated measuring device and I measured the diameter of an atom, for example, and I see that it's 0.00000000025 meters. So m there's meters, right? That is obviously a very small number, and it took me a while to write it. Okay, so how do we convert this into scientific notation? Well, first we need to do is to find the decimal point. And here we have an explicit decimal point right here. What we're going to do is we're going to move that decimal point either to the left or to the right, so that we end up with a number between 1 and 10. So in this case, I'm going to have to move my decimal point to the right. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. Right, so I end up then with 2, decimal point is here, between the 2 and the 5, so this ends up being 2.5. And then I'm going to multiply that, 2.5 by 10, raised to a certain power. And the power is how many places I have to move that decimal point. So I moved it 10 places. And if I had to move it to the right, okay, that my exponent there is going to be a negative value. So this ends up being 2.5 times 10 to the negative 10, and then one unit there, meters. So the way that we can tell that this number makes sense is if my power of 10 here, so this is the exponent, if that exponent is negative, that means it's a really small number. Right, so that's what this is equal to. This first part of it here, the number between 1 and 10, that is known as a coefficient. So when you write a number in scientific notation, you have two parts to it, actually three parts to it. You have the coefficient, the number between 1 and 10. You have 10 raised to a certain power, the exponent, and then you have a unit, right? That tells you what it is that you're actually measuring in this case. So negative exponent, a really small number. What if we had a number on the other end of the scale? So let's say we had a number like 602. And then a bunch of zeros here at the end, right? So we're going to do the same thing. We're going to first of all find the decimal point. If you don't see one in the number, it's understood to be here at the end, the very end. And then we're going to move it either to the right, to the left, to end up with a number, a coefficient, between 1 and 10. So I'm going to have to move it to the left in this case. So how many places to the left will I need to move my decimal point? So let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and then 23. So I'll end up with 6.02. That's my coefficient, number between 1 and 10. And then times 10 raised to a certain power. And that's how many places I moved. Decimal point, I moved it 23 places. And because I moved it to the left, I have to move it to the left. This ends up being a positive exponent. I don't need to put the positive sign, it understood. So I end up with 6.02 times 10 to the 23. That's this number here, which took me a long time to write, but I can write it more concisely using scientific notation. This value here with the positive exponent, that means that it's a really big number. And how you interpret numbers, you interpret values, just to get a sense of, is it big, is it small? Especially when you have a number inside of a notation, you just make up a sign of the exponent, right? Negative sign, small number. Positive exponent, large number. We need to develop that skill in interpreting your values. Okay, let me jump back up here really quick. There's something I forgot to address when it came to these exponents. So we talked about multiplying. We just added them. If we divide, we subtract. Sometimes you'll see some other things. So for example, if I had something like, let's say I had 49 raised to the power of half, right? And you'll come across that occasionally. So this here is the same as saying the square root of 49. And then in your calculator, you end up with 7, right? So you'll see numbers like these. Similarly, if I have, let's say 25, and then to the 1/3, right? What that is, think about it. Again, you can use your calculator to solve these if you wanted to. Right? You can use your calculator. I'm going to change this here, my left over one. So if I had 125 to the 1/3, that would be the same as saying the cube root of 125. Here it was the 49 to the 1/2. That's the square root of 49. 125 to the 1/3 down here, this would be the cube root of 125, which would be 5. Right? So 5 is 5. That's 125. Similarly, up here, 7 times 7 is 49. Right? That's the square root of 49. So the cube root of 125 is 5. But sometimes you will see these experiments that are like fractions. And these are probably the most common ones you'll see on here. And again, using a calculator, you can double check these, but developing a little bit of intuition is going to be important. Okay, so we talked about scientific notation, where we have a coefficient, number between 1 and 10, multiplied by 10 raised to a certain power. If that power is negative, that means the number was originally very small. If the power is positive, that means the number was originally very big. Right? And we're going to use scientific notation a lot when we get to dealing with more calculation, but also just looking at the relative sizes and amounts of different things. So let's take a look at how we can use these numbers in calculations. So let's say I had, for example, I'm going to have 2.5 times 10 to the 7. I'm going to multiply that by 2.0 times 10 to the 4. All right, so obviously you can use your calculator here, plug it in, and you end up with your answer. But again, working with the numbers, you can actually make your life a little bit easier just by separating out the coefficients. So for example, I can multiply the 2.5 by the 2.0. So this times that here is going to give me 2.5 times 2 is the same as 5.0. And then I can work with the exponents separately as well. Right, so 10 to the 7 times 10 to the 4. We know how to do that. So that'll be 10 to the 7 plus 4. So this then ends up being 5.0 times 10 to the 11. Right? So we can use some of the stuff we learned before with the exponents, how we interpret them. now we're incorporating it into scientific notation to solve some of these problems. Similarly, if I have something like, I'll do the same, something similar. Let's say I had 5.0 times 10 to the 9. I'm going to divide that by 2.5 times 10 to the 13. Okay. Again, I can tease out I can put these in parentheses there if you need to. I can tease out the coefficients first. So 5 divided by 2.5, that's going to give me 2.0. And now 10 to the 9 divided by 10 to the 13. So that's 10 to the 9 minus 13 because I'm dividing, I subtract them. So this ends up being 2.0 times 9 minus 13 is the same as 4. So I'll end up with 2.0 times 10 to the minus 4. So let's think about both of these values that I ended up with. So you get a number in both cases, but does that number make sense, right? So let's think about this. Let's ask ourselves, does it make sense? Well, I have originally here on the left side, hit 2.5 times 10 to the 7th. Based on what we calculated before, that's a large number. And then I'm multiplying it by 2.0 times 10 to the 4th. That has a positive exponent. That is also a large number. Right? So if I multiply a big number by another big number, I should get a big number as well. Okay, and how do I tell? Well, I look at the exponent, positive value. So yes, this does make sense. We take a look at the second one here. So I have a 5.0 times 10 to the 9. That is a fairly large value. And now I'm dividing it by 2.5 times 10 to the 13. So you will now notice that here the exponent is a much larger positive value. So this here is a larger number than we have in the numerator. So the numerator is large. And the denominator is even larger. So if I divide a large number by a larger number, I should get a small value, right? So it's like dividing, 10 divided by 100, right? You have a large number in the numerator, but an even larger number in the denominator. Well, 10 divided by 100 gives you a small value, right? 0.1. So just using that idea, we can predict that we should get a small value for our answer. Right, and here, -4 as my exponent, that tells me, yes, it is a small value, right? So as you're doing your calculations, and again, you're just essentially doing a bunch of math here the first week or two, getting a number is, yes, getting an answer is important, but then you want to think about that answer. Does it actually make sense based on just, what you expect to happen? Should it be a big number? Should it be a small number? Right, that will help allow you to check your answer at the end to see that it does make sense, or maybe it doesn't make sense. And if it doesn't make sense, and that usually means that you did maybe you subtracted when you should have added, maybe you added when you should have subtracted, etc. Okay, so you want to use, and again, this is something that you want to apply to all of the calculations that you do. Okay, does the answer make sense? There are different tricks and tips along the way that you can use to help you decide that it doesn't make sense.